This is more of a primer on how to do statistics, or how you can do statistics with EEG and MEG data. There aren't really that many great visual illustrations about statistics. At least I couldn't really find them in published literature. So bear with me. I think maybe this will be a bit wordy, but at the end, I will go through an MNE-Python example, which might also illustrate a few of the points I'm trying to make. So the simplest approach, I guess, is to use regions of interest analysis. This is quite common. You'll see that in many papers, and it's perfectly suitable if you have hypotheses about location and maybe time range of effects. So this is just one example, studies from our own lab. You define a set of ROIs here in the left hemisphere and only one in the right hemisphere. It's a language study, so you think most of the action is happening in the left hemisphere, possibly something in the right anterior temporal lobe. And then you do the contrast, you run the contrast that you are interested in. We compare two tasks here, and you can then plot the time courses for every individual region. So these labels here, they respond to the regions of interest. And you can plot the activity. So the colored lines here are the activities for two different tasks. You can look at the difference, and then you can also look at here the t-values. Okay, you can probably not really read the scale here, but these are t-values here that compare these two conditions with each other, simple t-test. And then you still have to decide how, I mean, this just shows you at an uncorrected level whether there is potentially a difference between these conditions. But as you probably know, there's the multiple comparison problem. The more tests you run, the more will be significant by chance. But just by eyeballing, you may see that some of these effects are not just randomly, sticking out of your data here. It looks like there is a longer time range with higher t-values. Not so much here. Maybe here there are some peaks that are higher than other peaks. Maybe a little bit more temporally extended, so they might be true effects, and so on and so forth. So, and you just want some criterion to take that into account. Some of these effects might be more long-lived or larger than others, so you want to establish a criterion, not just at the time point by time point level, but that also takes into account whether significant effects occur in the same latency range next to each other. And this is something that cluster-based permutation tests do. And yeah, I didn't really find much that would have helped me to visualize how this works. So I will just use the description here based on the Maris and Osenfeld paper that I will cite in the next slide. This here comes from the Field Trip Toolbox. I've slightly modified that. So the basis of these tests is that you define clusters based on either temporal or spatial adjacency of effects, or both. It could also be based on time and frequency, or time, space, and frequency adjacency. Anyway, you define clusters, and then you test whether these clusters are significant. So you define run some statistical tests on the cluster level to check whether or which of these clusters are potentially significant. So first of all, you have to define your clusters. And that means for every sample, and it depends on your data, it could be in space and time and frequency, or all of the above. So for every sample, you first of all need some metric that compares conditions or tests your condition against zero. That's often a t-value. So this is still at the single sample level. And it's important to highlight this is not the cluster-based test metric. So this is not related to the metric that you're going to use to check for cluster level significance later. So you could actually define clusters in a range of different ways. You could guess, I guess, where there might be clusters. But this is just the first step, at least. You have to have some values at the single sample level that later decides whether it's worth considering these samples as part of a cluster or not. And this is already part of step number 2. You then, on the basis of this metric, step number 1, you decide which t-values could potentially be part of a cluster. That means it's some sort of basic level statistical threshold to say, so which samples have potentially an effect that could be part of a significant cluster. Again, this is not related to the cluster level statistics in the next step. This just helps you to define which potential clusters there actually are. And then, and this is an important step, you select these samples that are connected, or that you think are connected in clusters. And that's where you have to define some sort of temporal, spatial, or spectral adjacency. So in terms of time and frequency, it's not that difficult. So time points, usually you just come one after the other. In terms of space, you need some criterion, and for example, for your sensors or for vertices in source space that tell you whether they are next to each other or not. And then you can compute a cluster level statistics for every individual cluster, for example, by taking the sum of the t-values within each cluster. I mean, other options are available, but then you actually need some statistical criterion or value that you can use to test statistical significance for an individual cluster. But then the actual significance test is by creating your own distribution of effects and checking whether your observed statistical values are actually at the upper end or the lower end of this distribution. So you create this distribution by randomly drawing trials from your data and assign them. I mean, let's assume you're comparing two conditions to each other. So you say it's subset 1 or subset 2. Yes, so, and this is basically the kind of where the permutation test comes from. So this, you're basically permuting the assignment of conditions and trials to trials in your data, and you're computing your statistical test just as before, as if your data were randomly, or your conditions were randomly assigned to your trials. Then you calculate the test statistics from above on this random partition. You repeat that many times. So every time you get a different permutation of your assignment, trials to conditions. So you can compute this many, many times, thousands of times, possibly even 10,000s of times. And with the values that you get from all these random permutations, you can construct a histogram of the test statistics. And then you can finally, when you think that you've sampled your distribution accurately enough, you can check whether your observed test statistics, cluster level test statistic, actually falls in the upper end, sort of in the less likely end of that distribution. Yes, and you can basically say what you consider significant then. So you then can define a p-value for this kind of random distribution that tells you if your observed value falls into that range, then it is significant with the probability of p that is often 0.05 or 0.001. And this was done here in this original paper. I think this is a classic paper that introduced this method to the world of EEG and MEG analysis. So this is illustrated here for a relatively simple case of one-dimensional data, just a time course, a bit like the example I had before. So you have an effect and you want to test it against 0. And again, you see that there is a peak here that's temporally extended. So you might get some significant difference here, t-statistic, that occasionally maybe goes over a level that at the uncorrected level you would consider significant, so above 2. But in some range, it's above 2 for a longer period of time, and you want to test whether that's actually meaningful. You can consider that as a cluster. So here you see the t-statistic here, the t-value, and then they indicate the uncorrected critical value, basically everything above 2. And they indicate the Bonferroni corrected value, which is over here. So in this case, you would be lucky. So even with conservative Bonferroni correction, you would get the tip of the iceberg here. It would be significant. Down here, it's also indicated what you get with your cluster-based permutation tests. So you would actually get, well, it's a bit hard to indicate here. So you would basically get almost this whole cluster here, significant, everything almost above the the uncorrected level. But the important thing is that this little dip here is not considered significant at the cluster level. Only the temporally extended peak here is considered significant at the cluster level. So that means it's possible to weed out sort of the little spurious effects, and you only get a significant, what is really significant over a longer period of time. And if we go back to these real world data here, so these are different regions of interest, different time courses, so different comparisons between two different tasks here. Again, this is the t-value here, this black line here. You can see that in some, I mean, it's quite relatively noisy data, so that's what you get in language experiments. T-values go up and down, and sometimes they are maybe a bit higher than, okay, sorry, the scale of the t-values here. So this is the value of 2 in this case. So sometimes you might just reach the value of 2. That would be significant at the uncorrected level. But when it is above 2 for a longer period of time, even if it's just about larger than 2, then this will be detected as significant. And then there are other cases where the t-value might go much higher than for up to 4 or 5, but for a shorter period of time. But this is then also detected as a cluster. It might be a shorter cluster, but the values are larger. So both of this is taken into account, the extent as well as the actual t-value. And then there are, of course, also cases that are highlighted here, slightly different shading, which you can consider as marginally significant, so just below the threshold. So this is indicated here. So their p-value is 0.05, 0.075. So you still have the problem that you have to define a statistical significance threshold in the end. This is also something interesting here. So you see this effect here. These two clusters here are separated by just a small gap where there was a non-significant effect. I mean, this happens. So because there are some samples here that did not produce a t-value above the threshold. That means these were not assigned to any cluster. That means you actually get these two clusters, and you have to decide now whether they are actually two separate clusters or whether it's just sort of by chance that there were a few samples that were not significant. So you would maybe have to go back to your data and check whether the topography changes over time. So these cluster-based permutation tests, of course, they still leave a lot to interpretation, but at least it shows you that there is something that at the cluster level that can be considered significant in these latency ranges. So we might now be tempted to conclude that our effect really lasts from this latency here, whatever this is, maybe 400 milliseconds, to the end here. Could be 750 milliseconds. But here we really have to be careful, because we tested these clusters based on a summary metric, let's say the sum of t-values across the whole cluster. Means all we can say is that something in that cluster is significant, but we can't say exactly which of these samples is significant individually. So that means we cannot draw conclusions about exactly where this cluster begins or where it ends. By definition, these samples here at the beginning and at the end of a cluster are just about significant here. So they're just above the threshold here, they're just above the threshold here. So these are the noisiest of our data points. So that means they're also the least reliable. So we can somehow probably conclude from this that there is a peak here in this distribution. And we know, of course, the number of vertices, or the exact vertices or samples that went into this cluster. But again, we cannot conclude exactly what the latency range or the onset and the offset of this cluster is. And this is something that Hassanhagen and Drashkov looked at in more detail. And I'm just going to summarize this here. So the title already basically presents the conclusion. Cluster-based permutation tests of MEG-EEG data do not establish significance or effect latency or location. All you know is that there is something significant within the cluster, but not exactly where in the cluster. And they simulated some data, some simulated ERPs, again, one-dimensional. And they estimated the earliest point included in any of the significant cluster based on different runs with their permutation tests. So every time they compute a permutation test, they got a different onset or a different cluster size, and they used the onset of that cluster to determine the onset of that latency. And if you look at the distribution of this, I mean, then you can see it's quite wide. So it's a very unreliable estimate. So the real onset is indicated here, but if you then simulate these data again and again, every time you run your cluster-based permutation test, you determine the onset. Then you get a distribution that sometimes can be, up to 100 milliseconds or more off the real value. So this is the distribution of the degree of underestimation. So if you're interested in the onset, yeah, so even values above 100 milliseconds have been observed here. So that means these cluster-based permutation tests are really not a good way to determine the onset or offset in effect. So that is something you would then have to test separately, maybe using some more assumptions you have about the type of data you've got. So this paper makes some suggestions there. So at this point, I would just like to leave it here. And this can be applied to much more complex data. I mean, obviously in sensor space, you can run your cluster-based permutation tests and say, hey, we found a cluster that has maybe 3 sensors on the left and a few more sensors on the right. You can do that in source space, which then tells you that there's a certain cluster here, probably around auditory cortex in the left hemisphere. You could also do this in the time, space, and frequency domain. I don't have an example for that. And no, not yet. I would actually like to show you just how this works, or what kind of pre-processing steps you need to make sure that at least that they have worked if you're applying this to real data. So I'm again using one of the great tutorials of the MNE-Python software. This is the cluster 1 sample spatial temporal tutorial here. And I will present this relatively quickly. So first of all, you have to specify some parameters here as before. In this case, they already say that they are only reading 300 milliseconds after the baseline to reduce multiple comparisons. So the length of your time interval obviously determines the number of samples that will go into the definition, and also possibly the significance testing for your clusters. So the fewer, I mean, you have to choose these things in advance, what's meaningful or what makes sense to you. The longer your epoch, the more conservative your tests are potentially, but at the same time, you might miss something that's outside this epoch. So there are still choices to be made. Then you define, okay, I should also point out, because the sample data set only consists of 1 participant, so they say that here, I think, they are actually simulating a multiple subject data set based on 1 subject's data. So don't take these things too literally here. So this is really just to illustrate the workflow. So please check in your own analysis if that all makes sense to you. So here they are creating epochs 1, epochs 2 for 2 different, what they then pretend are 2 different conditions for your 6 subjects. It's important that if you do this in source space, that you transform your data onto a common source space, a common cortical surface and free surfer, for example. You might use a volumetric source space. In this example, they are doing it in a slightly sort of on-foot way. So they are using here okay, let me just check. I mean, they're basically reading the data into a matrix, into a big matrix X, which contains all subjects across time and across space. And then they are applying their morphing procedure to these data. You might have done this already beforehand in a separate step. So you might have morphed all your source estimates already to a common, to the free surfer template, for example. Then you just have to read these data here. But at some point, at least, you have to, you must have transformed all your data into a common source space. Otherwise, you can't really compare them across participants. And then the art, or the important bit, is to put all your data into 1 matrix, which they call X. And this contains your data across, in the end, across subjects, number of time points, number of vertices, and you might also have number of frequencies there. In this case, this is not the case. And in this case, you have 2 conditions. There might be more conditions if you're running an F-test. There might even be just 1 condition if it's a t-test against 0. But in order to then define your clusters, you need an adjacency matrix. So you have to make sure that you have a way to determine which samples are adjacent to each other. In time, there's not really a big problem. In frequency, neither. That almost comes for free. But in space, you have to make sure that if you are in sensor space, that you have a way of determining which sensors are next to each other, and in source space, which vertices are close to each other. And luckily, I mean, there are functions in MNE-Python that do that for you, but just to make sure you're aware that this is something you have to sort out in advance. And then you are ready to compute the actual statistics. You have to make sure that your data, I mean, this important matrix X has the right dimensions. So in this case, the first dimension has to be subjects, then time, and then space. So this is done here. You need the parameters for your statistics. You need a p threshold, degrees of freedom, and because the actual cluster test here requires a t threshold, you have to compute the t threshold based on the degrees of freedom and the p threshold. So that's just an extra test you have to take. And once you've got that, well, you run it. It'll take a moment. And then you have some, well, it outputs you some numbers, which tells you which cluster it found and the vertices within each cluster. But of course, you then want to determine which of these clusters you consider significant, depending on your significance threshold. The threshold above was for the single sample level. So it was not the test. This was not the statistics for the actual cluster significance. So here they decide that 0.05 is your p threshold at the cluster level. So you select the clusters that were significant at that threshold, and you keep these clusters. And then finally, very important, of course, you have to visualize your clusters. And that's, again, something where you have to put some thought in, because you have clusters that are now extended over time and space. So at this point, they visualize a summary of all clusters that they found, and all the good clusters, all the significant clusters. So there's a way to summarize these clusters into one source estimate. And well, what you get at the end is a plot like that. And here they actually plot the temporal extent. So you have the color here just basically tells you for how many samples, or actually milliseconds, how many milliseconds every vertex here contributed to a significant cluster. So it tells you where the extent of the overall cluster. So all these values, at least at some point, contributed to this cluster. And it also shows you those that have contributed for the longest. So here at some of these peak locations. So you can now also, of course, go into these clusters in more detail and plot them over time, potentially analyze them in more detail. For example, if you're interested in something like onset and offset of clusters, but the same logic or the same caveats that I talked about in one of my previous slides, of course, apply here. So you cannot conclude that the cluster really extends only from here to over here. So you only know that this cluster as a whole, the summary statistic, is significant, but you can't really say which individual clusters here are significant. In this case, you have a priori knowledge. So this was the auditory condition. So you know that you expect something on auditory cortex. But if you really want to extract more detailed information from this, from these kinds of data, then you have to put some more effort in. I should also have mentioned, I think I forgot to say earlier, they also cropped the epoch to go from 0 to 300 milliseconds. That means what this here tells you is that, I mean, or let's say all that this tells you is that this cluster or something on the cortical surface contributed to a significant cluster somewhere between 0 and 300 milliseconds. So you don't really know at this point where or when in time these different vertices contributed. And again, you also cannot exactly be sure where the boundaries of this cluster are. You just know that there is something significant here around auditory cortex. Okay, yes, and the other clusters, yes, I mean, the MNE-Python gives you this first summary cluster as the first sample in this source object, source estimate object, and it gives you also the other clusters as a source estimate as different samples here in the source estimate object, so you can potentially also inspect the other clusters or the individual clusters. So this was really just a quick overview of how this can be done with EEG and MEG data. Of course, there are lots of details that could all be discussed in much more detail. And this is something that actually papers and maybe other presentations are for.